welcome back to Voxtelesys informational videos. This video we're going to be discussing firewalls. The previous video we were discussing the basic networking infrastructure, and so in this video we're going to dive deeper into what makes properly configured firewalls. So a firewall does network address translations. You can do access lists or rules. Things like ALG, VLAN, and QoS are a big component to ensuring that you have a quality voice solution. So we're going to be addressing each one of those, as particularly how it relates to the voice applications that we service. So in the previous video, when we were talking about the public network, we broke it out a little bit more detailed about IPv4, BGP, AS numbers, routers, modems. We're going to tie that down. So what we want you to assume is that the BGP is part of the public internet and the router and modem are part of the public internet. We're just going to represent public internet by this cloud, and that's it. We also discussed the OSI model. Keep that in mind because it still is at play here, and it's a big part of how you should be considering how you should be looking at how packets traverse the network. So let's get started. So right now, Google sits outside the public internet. So if you want to go to a YouTube or if you want to go to a Google search, you have to go through the public internet to get to it. So in this video, we're going to discuss NATing and how ICMP would NAT through your network so that Google could then respond to that ICMP to tell you that it's there. So the public internet is plugged into a firewall. In this demonstration, we're going to use the 1.1.2.1 publicly routable network as an example. It is not something that I have. I'm just using it as an example. In this example, we have a static route, and it's a /29. So the firewall is .2. The carrier is giving me .1, and I have a default route pointing that anywhere I want to go in the world, I have to go to .1. And that's over the WAN interface. We then have the private network, and for this demonstration, we're going to give it the network address of 10.10.2.1 as the firewall. The network space is 10.10.2.0/24, so it gives you a full 255 network, 254 addressable network hosts, and we are going to then plug in a masquerade that says anything from 10.10.2 network, change the source of that to 1.1.2.2 for the public internet. And then we're going to plug in our computers. In this demonstration, our computer is going to have an IP address of 10.10.2.101. And if we would like to ping Google, what we're going to do is we're going to open up a console. We're going to start a ping by typing in PING. And the destination is going to be google.com. What's going to happen is ICMP is going to, once again, we talked about the OSI model, layer 7, 654.321. So you've typed in ping, that's the layer 7, and then it's going to get that all the way down to the binary and place that binary on the wire, or on the medium to get out to the LAN. So once it's hit that layer 1, it goes up to the switch in layer 2, and then from layer 2 it goes over to LAN because the MAC addresses are in the same broadcast domain. We know how to get to each other. Once you hit the LAN on the firewall is going to see that, first off, it's coming from a source of 10.10.2.101, and there is a NAT for masquerading at 10.10.2.0. So it says, oh, I need to NAT this because he's going to a publicly addressable name because Google's out in the public internet someplace. In this case, let's say it's 8.8.8.8. That's their publicly available DNS server. And it's going to say, oh, I know how to get to that IP address. Now remember, host names don't route, only IPs do. So when I ping the destination of google.com, it's going to translate that into a publicly accessible IP address. So the firewall then says, okay, I'm going to convert the source from 10.10.2.101 to 1.1.2.2. And then it goes and sends, the source has been created. It then creates the ICMP, the ping event, to the destination of google.com. Now, when Google responds, they're going to not respond to our 10.10.2.101. They're going to respond to 1.1.2.2. The firewall is going to receive that, knowing that I have made that event ping because there's a session in there. It's going to then forward that request, that response, to the 10.10.2.101, and it's going to translate it back to the source IP. So that's what the masquerading does in NAT, and this is the simplest terms of how it works. So let's look at a ping trace real quick so that we can actually understand a little bit more of this. So let's go ahead and type in ping. So what's going to happen is ping is going to resolve Google to an IP address, a publicly routable IP address. So as you can see, the publicly routable IP address for Google is 172.217.164.206. And as I described in the diagram, my source IP is .101. Once I hit the firewall, which is my default gateway, it then says, okay, I'm going to route through the firewall and NAT the source IP to 1.1.2.2. Now, the response we're getting back from Google, because what you're seeing is a response from 172.217.164.206, that response is coming back to the publicly facing IP address of the firewall, which is 1.1.2.2. And then the firewall is translating that back to 10.10.2.101 in response to the originating ICMP. So there has to do a trace route on that to keep hold of that. So I hope this has helped. Makes sense. And let's get back to the drawing. So we've identified that you can go from a computer that's on a private network, a non-publicly routable network, to a firewall that has NAT enabled properly, and then have that local address translated to a public address, and then have a public network device like a DNS server or a search server respond to ICMP. And it works much in the same way for most other things. So let's talk about your access lists and rules. They're very simple. It's the principle of blocking or denying or allowing access to and from based on source and destination IPs. You can apply those rules on the LAN side or on the WAN side. Typically, if you're blocking on the LAN side, you're blocking. If you want to block traffic going out to the public internet, you're starting the access list on the LAN side. If you want to block traffic from coming into your firewall, you're doing it on the WAN side. That's a pretty basic principle. So what we're going to do is start by showing you how you program an access list. We currently are a huge proponent, and probably will be for the rest of my life, of open source software. So we'll start off by using a pfSense firewall to demonstrate how we tie all of this together. All right, so I have my pfSense firewall rules opened up, and I have a terminal window opened up so that we can discover some things about the network before we move forward. So what I'm going to do is demonstrate how you block traffic. We're going to use ICMP, the protocol ICMP, as an example because it's the easiest way to show. First thing you need to do is find out the IP address of your computer. I use Linux, so that's done with host name -i. As you can see, I'm on the 192.168.26.131. I prefer, personally, and I recommend most network engineers do this, is to actually do a grep of your INET. This allows you to see which actual interface you're getting. So in this case, my laptop can actually have 5 or 6 IP addresses on it, so it's always best to know which one I want to use. So my source is going to be this wireless network, and I can see that I actually have this 131/24. Broadcast is 255. The implication of that is that you know what your route is. You can go type your route in, and now you can see that your network is on the wireless, and my default route is .5. So this is stuff that you need to know when you're dealing with networking, is what your source is, what your destination is, and how you're going to get there. And so in this case, my source is .131. My destination is going to be pinging Google, and to get there, I'm going to have to go through a .5. Pretty simple. And you can also see that I'm using DHCP. All right, so back to the firewall here. So now that we know my IP address is the 192.168.26.131, we can go and add a rule. When adding a rule, you have your options between pass, block, and reject. Pass is to allow the traffic through. Block is to block the traffic. Reject is to reject. If you're using a TCP protocol, it will send a rejection. The interface that I'm applying this rule to, so I don't have the typical LAN in this environment. I actually have multiple of VLANs, and then I assign each group to those VLANs based on the requirements of that team. But for this sake, the dev VLAN interface is going to be the LAN side. It's the local area network that I'm working on. My IP address family is IPv4. The protocol is going to be ICMP. And then in ICMP, you have a bunch of subtypes. We're just going to block anything for the description, but as you can see, there's a ton of things you can do with that, but that's not the source of this conversation. As far as sources and destinations go, those are pretty simple. On the source side, we're going to select a source host or alias. A host is going to be the IP address of 192.168.26.131. You could also put in a host name in there, google.com, but it's still going to resolve that using DNS to an IP address, because remember, we only route by IP. So in this case, we're going to set in a IP address. Just note that when blocking in a firewall by host name, there's a chance that that name and IP will change. So for example, my laptop might get a new IP address and then advertise out a new name with a dynamic DNS, and then the firewall is going to have my old IP, and I'll be going through just fine because of that. You want to be explicit when blocking. So for this example, I'm using a IP address of a DHCP server, but in real life, you would want to make sure you tie that down either through a MAC address to DHCP requirement in your switching, or something along those lines, or just block the entire network. And you can do that too. So you can say, block the network, and so you do the 192.168.26.0/24, and that will block the entire subnet of that network. But in this case, we're just going to block the IP address because I don't want to destroy everyone else on the network. All right, so 131 is the network address. The destination is any. I don't care where we're going to. We're going to reject. And actually, as an initial rule, we're just going to say we're going to reject any. All right, so this is literally anything from this IP gets blocked. We don't care about anything. That's the root of what an IP access list is. This IP is not allowed. We are blocking or rejecting. So I can transition back to my terminal here. And we're going to do MTR, which is a version of ICMP, but I know we're not using ICMP at this moment. And we're going to go, all right, failed to resolve because I can't actually get to DNS. So let's transition back. So if I want to allow, I can copy this rule. We're going to put this up, single host. We're going to go pass, and we're going to set TCP UDP, and we're going to go to DNS. Is that correct? Yes. All right. So now that I've applied that, we can switch back to my IP and DLS DNS. Oh, nope. Actually, I can tell you what I did wrong. So as you can see in the position here, my rule is below. So you have to move this rule up. And now we're going to apply. So we're doing the MTR, so I was able to resolve the address, as you can see. But because I can't get past the firewall, because the only thing I could do is DNS, it's not going to allow me through. So let's transition back. Let's go and we're going to clone this rule. And instead of TCP, we're going to allow ICMP. We're going to say any, hit save, apply. Okay. Now we're going to transition back, and as you can see, we now have a full trace going on. And the best thing about this is that you can see, in this case, I denied everything in the firewall here. So I'm saying anything from this source, 192.168.26.131, and it's going to be blocked. But then above it, I said, but if they want to go to do ICMP, we're going to allow that. And if they want to do DNS above that, we're going to allow it. It's pretty simple stuff, but it's pretty powerful because you can see how you can structure this. The other thing you can do is go by source. So we're going to transition back. All right. That's right, I can't do that. So I'm going to ping Google, and you're going to see this 206, this 172.216.164.206 address. Okay. And we're going to transition back. Let's go over here, and instead of having a source address in the ICMP here, what did I do wrong? I know exactly what I did wrong. I did not put an allow for my IP from this computer that I'm working on to get to that, because it's in the dev network. It doesn't have a default allow. So I've actually locked myself out of my firewall temporarily. It'll take me 2 seconds here. All right, we're back. And let's go back to the rules. What we're going to do, just for the sake of not having a headache, is we're going to add, and we're going to say, all right, so that's in there. So we're now allowed. Give me a second here to go fix this. All right. So now we have this. Actually, let's make sure that that's all good. Oh, we're good. All right. So now we have 4 in here. We're going to go and modify this rule here, this ICMP rule, not to be the host. We're going to say any host. And a single address. All right, and we'll be able to, now we can ping Google, as you can see. All right, but we can also we're going to MTR Google right now. So as you can see, I'm MTRing it, and we're going to transfer back. And what I'd like to do is, so we have this IP address, this resolution to 206. I'm going to temporarily disable that. Okay, so that rule's been disabled. As you transition back, you can see that it's not going to work. Now I can go re-enable that rule. And we are good to go. So you can kind of see how powerful this. Now we're kind of interchanging IP access list rules by messing with protocols, and not just having I showed you an any block of the IP address, showed you how to put things above it. You can block if you know for sure what a source is and you know for sure where the destination is. Then you can block by IP. If you just want to block by port, you can do an any block. You can block any IP from anywhere to anywhere based on a protocol. So setting up access rules is very powerful. I would say 90% of our customers, the thousands of them out there that we've talked with, they don't do much in their firewall. I would say more than 90% of them don't even modify their outbound firewall rules. It's just any, and that's fine. I mean, the real thing is you don't want the public talking to the private, but the more you get into your voice networks, being able to do things like logging and quality of service, a lot of firewalls offer that. So, for example, you can come over here and you can enable logging on this, and save that. And now you're going to log all the data on that, and so you can log ICMP or DNS requests from the 26.131, and it just means that you can know more about what's going on in your network. In fact, if you followed the news recently about security, you had that big breach where SolarWinds had a default password that was like default 123 or SolarWinds 1234 on their deployment server, and so there was foreign entities that were able to penetrate that product and submit changes that were then pushed out to many of their customers, not all of them. And it wasn't necessarily as bad as you think it is. It was bad, but it wasn't like, the problem is with SolarWinds, if you use their Orion product, is you're kind of giving it God access to your network. But if you were to have securities in place and loggings in place, you would have identified, hey, what's going on? Why is this thing talking to networks I don't know? And the logging would have been able to identify those problems maybe before any damage was done. So this is access lists in a nutshell. All right, let's talk about, I know ALG was next in the list, but we'll come back to that because it's a little bit more complicated. Because it's kind of an add-on to NAT, and but we're going to come back to that at the end so I can show some examples. Let's go right into VLAN and QoS because it's kind of where we're at in this part, and we'll talk about it. So VLANs are a little complicated. They have to be configured at firewall, switches, routers. Anything that's going to be touching it needs to know about it. So let's just go over what it is. It's VLANs are 802.1q. That is a protocol that exists inside of a IP packet. So you have your preamble, your destination MAC, source MAC, the type, the MTU, FCS, CRCs, and the interframe gaps. All of that stuff is what those bits, those little fiddly bits to get put on the medium that goes across layer 1. That's how you get to that from layer 7. Where VLANs come into play is the 802.1q is inserted between the source and the type, and it's I think it's 8 bytes. It's 8 bytes, and so that information is telling it a VLAN number. There's some other information that goes in there to allow that VLAN to work. So what you're doing is what 802.1q tagging is, you're tagging a frame, you're tagging the packet and say you exist in this subdomain, network domain, broadcast domain. And so by creating these broadcast domains, you're isolating out how a switch treats traffic. You're also able to create multiple interfaces. So for example, in a firewall or in a router, let me transition over to this. You can set up VLANs and you can tag a port or untag a port. Now, untag just means that the 802.1q is pulled out, but the physical device, the layer 1 port is transmitting on that VLAN. So the physical device you plugged into is actually transmitting. The layer 2 transmission is all done on as if it was on the VLAN. So an untagged VLAN, for example, we have 1.2.133 is untagged on 150. So it's just going to think it's on 150. But then on top of that, I have tag ports like 40, 44. So those ports, you can still access VLAN 150 by tagging in the frame. And so there's information that's in that. So in that 802.1q data, we actually have information that's directly related to the packet here. So you have the tag protocol identifier. I think it's the TPID. That's a 16-bit field. You also have a TCI, the tag control interface. This is probably going way deeper than we need to for this. The key thing is you have the VLAN identifier, which is actually the number, so VLAN 101, 102, and that gives you the ability to assign a VLAN number to a field on 802.1q or a port to a VLAN. There's a priority code. It's you can service map priority levels. It can be used to prioritize traffic. So you can say this is a prioritized VLAN. So if you want to prioritize a voice VLAN, it's a form of QoS that you can throw on a field. It's not what we're referring to like a DSCP code, but it's a form of QoS, and a lot of people will create a voice VLAN, and that's important. So for example, if you want to put an IP address for a phone in a voice VLAN, you would tag that phone to the voice VLAN. So let's say the voice VLAN is 160. So you're going to tag that phone into 160. Now it's going to go out. You're going to assign it to 160. It's going to come back, and we'll go into more detail of that in a future video where how to assign multiple VLANs to a phone, and so that you can do quality of service and some other beneficial things. And there's some specific configurations to keep in mind. But in a nutshell, that's what a VLAN is. So we talked about VLANs, and we talked about that there was a QoS or a prioritization within VLANs. QoS is, when people talk quality of service, there are three ways you can prioritize traffic in a network. You can do it at the VLAN level. You can do it through prioritizing traffic through your router or firewall. And then you can do a TOS, diffserv, DSCP tagging within the frame, and then set that the devices on your network that are aware of that will prioritize that traffic through your network. Diffserv does not, that TOS, diffserv, DSCP does not go into the public internet. It never makes it past your firewall. And if it did, the public internet, unless you have some kind of dedicated service or a MPLS service, it's not going to get recognized across that network. So let's talk about what we do know makes it here. So DCP, diffserv, TOS, there's others in there. You would set that at the in the header file of your IP packets. So for example, we have one that's a DSCP 46. You put that into your code, you do some translations. We'll put that in the Mango statement of an IP tables. So it tags that into every frame so that our switch, our Brocade switch, will actually accept that TOS tagging and prioritize that traffic. That is wonderful. That works. To be honest with you, most people end up setting the TOS at the VLAN level in the 802.1q, because when you set it at 802.1q, you're basically saying anything that's on this VLAN is prioritized. Now, that is assuming that your network, so that there are some assumptions here. This is not gold, but if your network is properly sized as far as infrastructure using managed switches, you can prioritize a VLAN within a switch. You can prioritize a VLAN within a firewall. So, for example, we can go back to, and you can do it in the switch side of things. You're kind of in this thing where you have these VLANs, and you can go. So you can go into your VLANs and you can see your priority level. So priority level 0. Well, you can elevate the priority level based on what you're trying to accomplish. So each one of these VLANs can have a different priority level so that you get different capabilities. It's important that you understand how that works. And And then the same thing goes with your switch. Sorry. Let's just do this. There it is, toss. So you can also set your 802.1qp prioritization within inside of your network and see the different bits that are set. So I've enabled it. We're listening to DSCP codes, and we're listening to 46. We're listening to some other stuff, and giving it the prioritization it needs. So like 46 is a prioritization of 5, and this is just so you can set your VLAN because your TOS or your TOS or your DSCP codes. I hope that makes better sense than maybe I'm expressing it. And then if you go into your firewall, getting away from this, I would say that setting prioritization at the VLAN level and then setting prioritization within your firewall by prioritizing the VLAN, to a 5 and prioritizing the traffic through your firewall, that'll ensure that internally your network operates. But as long as the VLAN at your firewall is prioritized, it will get first right to go through your network. It's an important thing to remember that quality of service can be set at multiple levels. I don't want to say that it's too complicated for the average person. You can set it on your phones. You can set it on your switch to do your DSCP codes and everything like that. But the truth is, if you set it at the VLAN level and tag things into VLANs, then it's much easier to view that traffic for what it is and understand it, unless you're going to crack open the monitoring tools to look at how you are, or if the switching infrastructure you have has the capability of showing you how you're prioritizing your TOS bits. So, once again, this is a nutshell. This is not meant to be an in-depth conversation about QoS. It's more of just to explain that the capabilities are there. And for small businesses, especially when you're dealing with the 10 to 150 size group, VLANing prioritization is probably the best way to go. All right, so let's circle back to the SIP-ALG and portion of this conversation. I know we said we'd get to it at the end, so let's just go over this real quick. On the far right of the screen, you see that we have a 3CX. It's plugged into a switch, which is plugged into a firewall, which then has access to public internet. For this demonstration, we're using a demo lab. It's off of a Cisco RV325. So we have your 3CX. It has an IP address of 192.168.1.150. The firewall is 192.168.1.1, and then we'll be accessing it will be translating that via NAT to a 209.243.1366, which is a lab network. And then we're going to have a phone that registers to the 3CX, which is an important, and we're going to make some outbound test calls to a SIP trunk so that I can show what SIP-ALG does. Now, 3CX, you're putting the public IP address of 209.243.1366 into the config. So it's going to modify the majority of the SIP header. You don't have to worry about doing that, or if you're using stun, it's going to modify it to the public IP address. What SIP-ALG does is that if a SIP header has privately facing IP addresses in it, it will convert those into publicly facing IPs, and it will make sure ports are properly set up. This is a very generic explanation of it, but I just want to show you how it works real quick. So 3CX plugs into a switch, plugs into a firewall. It has a private IP address. It gets NATed to a 66 through the public internet. Let's go here. So now we have your Cisco firewall. By default, it usually comes with SIP-ALG enabled. Let's log back in. So let's go to firewall, general, SIP-ALG. All right, so we're going to turn on SIP-ALG so I can quickly show you what's going on. Let's grab a trace here. All righty. All right. So this is the private side of the SIP, and here is the public side of the SIP. So you're seeing this from both sides of the equation. All right. So we're looking for SIP on host 266 on the public side, and on the private side, we're just looking for everything. So this is just running on the 3CX server. We're looking at all the SIP traces coming in out. So let's go to alrighty. So now we have the SIP traffic up. All right. Let's go back to my trace here. All right. So as you can see, we have a invite on the public here. And in this invite, we're going to open that up some more. All right. You can see that there's a VA header here, and it has a publicly facing IP address in it. On the private side, this is the call from the phone, and this is the actual outbound invite to the carrier. You'll see that the invite here, let's go expand that some more, has a private IP address in it. So you can see the two different, the two different systems here, where it's the firewall is the only thing between the 3CX and the carrier that can be modifying this. Now, if this didn't have, if 3CX didn't modify the private IP address to a public IP address, the 209.43, the 66 down here in the audio SDP area, then the call wouldn't work anyways. You need to modify that in your PBX. But what happens is that because the firewall is modifying the SIP header, a lot of times it will modify things you don't want it to modify, and it will break your phone system. So it also, so if you're having one-way audio, it's because it's not properly modifying it, or you have too many calls up, or there was some contention and it broke it. On the flip side of things, that if your calls are coming, if you're trying to have a long phone call, there's invites in the middle of that, re-invites in the middle of that phone call that, hey, let's keep this call alive. And for some reason, ALG will break it. So all carriers that do PBXs, Avaya, 3CX, FreeSwitch, their derivatives, Mitel, they all require you turn SIP ALG off in your firewall if you want their products to work through it. So you see that, right? Let's go back and show SIP ALG turned off. All right, let me go grab the firewall here. We're going to turn that off, save it. Good. So now we have that next call. So grab my keyboard back. So this is the outbound call to the carrier. This is the inbound call from the 3CX. And you'll see in the SIP header, let's expand this out. Expand that out. You'll see that the private IP address is still in the VIA header. Now, SIP ALG will mess things up, because it modifies, the firewall is trying to modify the SIP header. We don't want that. That's why you turn it off. The VIA headers are ignored by most SIP products. That's why 3CX doesn't modify it. But that was the easiest way for me to explain this, of what's going on. You don't want the firewall actually cracking open your SIP header, which was set at layer 7. Remember, layer 7654. It's all prepared up there. That header was set at layer 7 by the SIP itself. And then you have the firewall breaking it open. ALG is actually modifying that above layer 3. You don't want that, or layer 4 even. You don't want it modifying your packets in any way. So that's why you disable SIP ALG on a 3CX. I hope that made sense. I hope that kind of brought to attention of what's going on here. And I hope this was a useful video. And next time I'll try and keep things maybe a little bit more compact and not do such a big presentation. But firewall is a pretty complicated thing, and it's not easy to break into chunks. So hope that helped.